A rational decimal terminates at some point, or it has a repeating pattern. And just to remind you, when we say terminate, we mean end. So if you have a decimal, doesn't matter how long it is or what it looks like, if at some point it stops, and for example here it stops at the 9, there are no other numbers being written, this is a terminating decimal. And a terminating decimal is a rational decimal. And essentially that means that you can find a way to write it as a fraction with one integer over the other. The simple strategy for terminating decimals to turn them into a fraction is to just write out the digits you have and then write out some power of 10. The power of 10 that will always work will be the 10 with the same amount of zeros that there are digits, and then just another 1 attached. A simple example would be 0.5. That is the same as 5 out of 10. A repeating pattern in a decimal is not just some pattern that you can discover, it's a pattern that will repeat itself over and over and over again. So for example, if you had 0.123 and this line up here, which is called a vinculum, if you have that, it means that its repeating pattern is that chunk of numbers 1, 2, 3, 1, 2, 3, 1, 2, 3. So not only does it have a pattern that's going up by 1, which is not enough, but that repeats over and over again. For example, 0.3 repeating. Well, this also has a repeating pattern where the 3 is just repeating over and over and over again. But for example, if you happen to see a decimal that was going up, in this sequence right here, well, if we kept going with this, yes, there's a pattern where it's going up by 1 each time, but it's not a repeating pattern, so this is an irrational decimal. And that means you couldn't find a way to write it as a fraction with one integer over another, or you couldn't find a way to write it as a rational fraction. How do you deal with these? Well, a quick way to write any repeating decimal as a fraction is kind of fun. You write down the numbers that are repeating, and then you just write over a number of 9s that matches that amount of digits. So with 1, 2, 3, we just write 1, 2, 3, and then 3 9s because there are 3 digits in the pattern. And here with 0.3, you just take 3 and write it over 1 9. If you saw something like 0.4567 repeating, that would just be 4567 over 9999. And in fact, let's go the other way now. If we were starting with the fractions, any of these, how do we find out what their decimal is? Let's start with 3 over 9, and then we'll go to 1, 2, 3 over 999. What I think makes the most sense, what makes the most sense is to use some form of long division. What you do is you divide the numerator by the denominator. And what you're going to find is, okay, well, if I keep going, at some point I'll find a repeating pattern, or what I'll find is that this terminates. So we'll try these 1, 2, 3 examples. If you're given a fraction, and you can, simplify it. 3 over 9 is 1 over 3. I divided the numerator and denominator by 3. And then we have to do 1 divided by 3. 3 doesn't go into 1 evenly, it's larger than 1. So we could write 1 as 1.0. And imagine 3 going into 10 3 times. So 3 times 3 is 9. And then, well, you can't do this, but you can do, cancel that out. 10 minus 9 is 1. 3 does not go into 1. But we could put another 0 there and pretend we're going to 10, so it's 3 again. And already you notice that, well, 3 times 3 is 9. And we have this 1, another 0. A pattern is repeating. So if you have this number reoccurring over and over again, and nothing's changing, you can go usually 3 or 4 places. I'm sure it would be enough for any state test. A repeating pattern, and then you're done. You have a repeating decimal. With 1/2, you would notice that 2 does not go into 1, but put the decimal there. 2 can go into 10. How many times? That goes into it exactly 5 times. And you know you found the end when you reach a remainder of 0. And you no longer need to divide. What about 1, 2, 3, and 9, 9, 9? Well, we could do 123 divided by 999. And what we would find is that, well, 999 does not go into 123. 123 is much too small. But we know it would go into 1230, put our decimal there. And how many times would it go into it? It would go into it once. We'd get 999. And then we want to subtract these two, just like we did before in long division. And we would get, well, let's just go through this. 231. 999 does not go into 231. However, it does go into 2310. How many times? It goes into it twice. 999 times 2, well, you can work it out over here, or do it in your head. 2 times the 9 is 18. 2 times the 9 is 18, plus the 1 is 19. 2 times the 9 is 18, plus 1 is 19. 1998. Subtract the difference. Here we get 2. Here we have nothing. Take this away here. Okay. 1, 10/9. 1, 2/9. Nope. Oh, here, 3. Okay. Does 999 go into 312? Absolutely not. But it does go into 3120. How many times? 3. And if we kept doing this, we would find that this pattern would repeat itself. And in fact, we would have the decimal 1, 2, 3, 1, 2, 3. So what you're noticing is that you have a repeating decimal if you're never finding that this subtraction step right here gives you a remainder of 0.